My name is Imad Mahjoub. I'm a professor of computer science and engineering, and I'm also the director of the Mobile Computing Lab. I would like to welcome you to the Mobile Computing Lab. This is a very active lab. We have a very strong team of about 6 PhD students and 5 master students. And we're working on very exciting problems in mobile computing and wireless networking.
Okay, my name is Francisco Padrone. I'm a member of the Mobile Computing Lab, and I've been working on some research on VANETs, which are vehicular networks. Use the vehicles as data collectors to detect traffic congestions and integrate it into vehicle navigation systems so that people can avoid traffic jams. So what I have here, in order to program this, we developed a simulation environment based on simulator coexistence swans that I modified to accommodate my research on VANET. It's a simulation of cars going on a highway. Not pretty good drawings of them, but they can be made better. So I can just start monitoring this simulation, and I can interact with it. I can go and change parameters like I did just now. I stop the simulation for a moment so that I can interact. For example, I can click on this vehicle and I'm going to simulate that there's a breakdown. So I'm going to basically create a traffic congestion by doing this. So now I can let this go, and as you can see, I can see the status of my vehicles being changed as represented by that circle around them. So that red circle means that they know there is a congestion. They suspect there is a congestion. At this point, because it's very small, they're kind of not sure. So that's why you see them coming on and off. And as the congestion grows, they start getting more sure, and then you start seeing those yellow circles, which mean vehicles that know about that congestion even though they are not in it. And that's the whole idea, right? Like you're driving to Miami, and then you know there is a congestion 5 miles ahead. So because the vehicles are using radio to communicate with each other, there is a limit in the space that they can reach. So you can see these guys here still don't know what's going on. But as the traffic moves, the information starts propagating to other vehicles that are farther. So once you have that information, then every vehicle will know what's ahead of them, and that can be integrated to a navigation system that tells you the route that you want to follow. It can give you a different route depending on traffic conditions. The research on the traffic congestion itself, algorithms, distributed algorithms to detect those congestions with considerations such as security and privacy in mind. Work on the simulator to be able to prove these algorithms, and in the visualizer to be able to interact with the simulation. This is integrated with the work other people in the team is doing, like Mike's. We can have the simulator. Right now I have the simulator and the visualizer running on my computer, but the idea is that the simulator is architecture so that the simulator can be running in a different computer or even a cluster environment, which is one of the things Mike is working on.
My name is Mike Slavic, and I'm a member of the Mobile Computing Lab. The role that I play for the lab is in the area of high-performance computing and simulation. We do a lot of simulations here of wireless networks, VANETs, and wireless sensor networks, that sort of thing. In order to facilitate that, we have to have simulators, and the area that I work in is trying to make the simulators run really fast. One area that I do research in is something called parallel event simulation. All the simulators that we use are event-based simulators. So when we go to speed them up, one way you can speed them up is to run them on a cluster computer, or a group of computers that are all networked together. So this is called a parallel discrete event simulator. My job is to create them and make them work and make them faster. So right behind me is some slides from a paper that we just presented at a conference that outlines an optimization technique for a parallel event discrete simulation. The main idea of this paper is to take your simulation objects that are in the simulation, and as the simulation's running, decide what machines in the cluster they should be resident on and move them around to make the simulation run faster.